Today I'll talk to you about catalysis and some inspirations from nature. So essentially I'm a chemist, and I know that many of you are not. So actually, who is not a chemist here? So okay, don't be afraid. At the end, I hope that at least you will understand the title, okay? So let's start with organic synthesis. What's organic synthesis? You probably recall some from your college or high school drawing some structures, some reactions. But I don't want to bore you with that. Just I want you to remember that organic synthesis is a technology that enables to transform accessible materials to valuable products. So where does the catalysis stand for here? So such reactions often that we want to conduct, they do not occur on their own, or they occur, but they also produce some side products that actually which are essentially waste. So then a catalyst is a substance that enables to transfer a substrate to a desired product in a selective way, in a reaction that otherwise doesn't occur or it's unselective. And essentially catalysis, it's a powerful technology that is involved in the production of over 90% of chemicals and materials that we use every day that range from bulk materials such as fuels, polymers, and so on, to some fine chemicals such as antibiotics or agrochemicals. Okay, so where does the nature inspiration come from? So in fact, in biology, we also conduct organic reactions, but those reactions are catalyzed by enzymes. So essentially, enzymes are natural catalysts, right? So enzymes are just some macromolecules that can bind substrates and selectively transform them to products. And if you ever heard about enzymes, you also know that they are highly selective. And this is very true. If we look at reactions that our bodies or just some germs can do, we cannot do the same reactions currently in the lab. So for instance, such enzymes, so-called cytochromes, they can conduct very selective reactions on such fairly complex molecules, steroids, to produce different molecules such as hormones. And they do it very selectively. So enzymes are very selective, but only for their native substrates. So in case of non-native substrates, there's no reason that those enzymes are selective. Essentially, such enzymes conduct reactions on non-native substrates in an unselective fashion. So as here shown, such P450 enzyme again conduct a reaction to produce a random mixture of all possible products. But we have now this great technology called directed evolution. And this is essentially a Darwinistic evolution where certain evolutionary pressure enables us to develop an enzyme or a protein with required property. And without going into details, so if you actually follow the news, scientific news last week or 2 weeks ago, Francis Arnold from Caltech got a Nobel Prize, or I should say probably half a Nobel Prize, for this technology. So how do we use this technology? So we take this, and now something's wrong with the point. Oh, you can see. So we can take this unselective enzyme and then apply the technology of directed evolution and develop a very selective a variant of this enzyme that conducts this reaction in a very selective fashion. And I like this example a lot because the authors also showed that you can take the same enzyme, apply it a different selection procedure, and then you can develop a variant selective for production of another product. And this is a very impressive selectivity. If you are a chemist, you probably cannot propose right away a catalyst that could mimic similar selectivity. So enzymes are great, but the problem is that they offer only limited range of reactions, right? Those are the transformations that occur only in nature or in our bodies. But we, as chemists, we have a wide range of reactions that go beyond the biosynthetic reactions. So, for instance, this is an abiotic reaction, hydroformylation. So this is a fairly old reaction discovered something like 80 years ago, and it's one of the most important homogeneously catalyzed reaction. And it's used on multi-ton scale per year. And actually, it's involved in production of various materials that, from very simple building blocks. The only problem here, as I depicted, hydroformylation can easily produce 2 different products, or sometimes even more. So, and even though that this reaction is so important and so old, there are still big selectivity issues, especially if you consider a slightly different substrate, so a substrate with this double bond between carbons that is internal. So on both sides, there are some groups that are of similar size, and in such case, the catalyst has issues to differentiate between them, and essentially it produces always a mixture of products, where usually only one of the products is the target product. So in contrast, if we look at biology, for a slightly different reaction, but for a similar substrate, so with this internal double bond, the enzyme can conduct a highly selective reaction. And if we look closer at the active site of such enzyme, we can see that there are some additional interactions noted on the here that are between the substrate and the recognition site of the enzyme. So essentially, this part of the molecule, this carboxylic group, interacts with the enzyme pocket to pre-organize the substrate in such a way that it favors just one reaction pathway to form only one product. So we asked ourselves whether we can mimic such substrate pre-organization for those abiotic reactions for synthetic catalysts. So how did we do this? So this was our logic. So we take just regular catalyst, unselective catalyst. We take a recognition site, so a scaffold that can interact with a molecule in analogy to this motif in the enzyme. So this pointer is annoying. But essentially, you can see here, like at the top, right, that this molecule can interact with carboxylic group, right? So we take those 2 structural motifs, we merge them together, and we produce such a bifunctional catalyst that now has a recognition site and a catalytic site. And we can use this system actually for many applications where we use this recognition site for specific functions. For instance, let's have a look now again at hydroformylation of internal alkenes. So how does it work? So the substrate again has the carboxylic group. It can bind to the recognition site on one side, and then the other side is positioned at the metal site in a specific way, which favors the formation of one product. And indeed, this system works very well for such challenging substrates, which otherwise just produce a mixture of different products. So, okay, I showed you that we can learn from modes of operation of enzymes how to design a new catalyst. But we ask ourselves if we can approach the problem a little bit different. Can we actually teach native enzymes to do new tricks? So how did we approach this? So if you consider, we looked at heme proteins, so proteins that contain this heme cofactor, so essentially this molecule shown in the middle that contains a metal site in the active site. And then we know that the metal is responsible for the catalytic activity. And such heme proteins were shown to be a good catalyst for many transformations. So all those P450 enzymes are essentially heme proteins. So our idea was to swap the metal in the center from iron for a different metal. And then we know that in that way, and we know that the reactions occur on a metal, so if we introduce different metal, maybe we can go beyond the natural reactions. And besides changing the metal, we can also change this axial ligand that is delivered via the protein scaffold. So in that way, we can design arrays of catalysts containing different metal sites in the center and different axial ligands that are then surrounded via protein scaffold. And screening such arrays can be done in a multidimensional fashion and aiming at some abiotic reactions, such as, for instance, this so-called carbene insertion reaction, which is non-existing essentially in nature. We were able to identify the constructs that conduct this reaction, and we identified that the constructs containing iridium site in the center are the most active. So, okay, so we have an abiotic reactivity, but are those systems actually selective? And the answer is no, they're unselective, but that's okay, because again, we have the directed evolution technology. So we essentially, in a stepwise fashion, we can collect or introduce suitable mutation into the scaffold of the protein to generate a variant that is highly selective to produce the one product in this reaction. And we can apply different selection procedure during the directed evolution, and we can develop the variant of the enzyme that produces selectively the other product. Beautiful. Oh no. Okay, I guess it works to some extent. Okay, so we have abiotic reactivity, we have selectivity, but if we actually look at activity, so how many reactions, so how often the enzyme works, this is a pretty lousy enzyme, right? It does like 4 turnovers per hour, so most of the time it just sits and laughs at you, right? So we thought that maybe we can improve this parameter just via selecting a different protein scaffold that is naturally evolved to bind organic molecules. So again, as I showed you before, P450s can bind big aliphatic molecule. So we thought if we use this P450 as a scaffold for our enzyme, we can improve the activity. And indeed, already the wild type construct was more active than our most active previously developed systems. And then we can further evolve the activity again, just applying directed evolution strategy, and we reach the level of activity which is comparable to native enzymes in their native fashions. So this is actually amazing because those enzymes are red hot while working. Okay, so now the question is, are we already as good or even better than nature, right? We have a wide range of reactivity. We can use some tools from biology, from enzymes or biology to develop highly selective reactions. To answer that, let's look at the typical scheme, synthetic scheme. So usually when we prepare a target molecule, we need to perform a sequence of reactions. So how does it look like? So essentially it means that we perform a series of iterations of reaction, isolation, and purification. And then in each step, we introduce resources and generate some waste. And if we compare it to biosynthesis, there all reactions occur in parallel in a well-regulated metabolic networks of reactions which enable for a steady flux of materials and energy toward the target product without any isolation whatsoever. So we ask ourselves, can we mimic such approach in Flask, in a synthetic chemistry? In that way, of course, we prepare, we obtain more shorter procedures that are more efficient and generate lower amount of waste, but also such systems can go through otherwise unstable intermediates or very reactive intermediates that cannot be isolated and that we cannot otherwise use. And we can also imagine that in such systems, we can use the reaction cooperativity and leveraging. So where can we use it? Let's look at such situation where our molecule, we have a molecule that we want to functionalize at one site, but unfortunately, there's another site that is more reactive. So how do we usually approach this problem? So we go to multi-step procedures where first we subject the initial material to reactivation procedure that changes the reactivity pattern of the molecule where the target position becomes the most active or reactive. And then such pre-activated intermediate is subjected to the actual functionalization reaction. And last, the functionalized material is subjected to post-functionalization to recover the initial skeleton of the molecule. So, okay, you can say, yeah, it's effective, but it's not very efficient, right? We have two steps that just involve in pre-activation and post-functionalization. So we thought, why don't we approach this in a little bit different way? Why don't we use this strategy of networks of reactions where we can induce the equilibrium between the initial material and the activated intermediate? And this is together in the same flask with the functionalization reaction. So here, first, the starting material, this guy on the left top, is in the equilibrium with the activated intermediate. However, once formed the activated intermediate, it undergoes the actual functionalization reaction. Then the functionalized intermediate remains in the equilibrium, but now with the target product. And due to the dynamic nature of both equilibria involved, at the end, the whole starting material is pushed forward to form the target product. And in other words, what's proposed here is to construct such a network of reactions that enable to go around this high energy barrier for direct transformation. And in a model system, we focused on reactions of alcohols, which are common motifs of organic molecules, and which are often rather unreactive at certain sites. And then we can reversibly oxidize alcohol to aldehydes, which are much more reactive, which can then undergo functionalization, enabling, in the end, the overall functionalization of the alcohols without any isolation of intermediates and without any additional reagents. So in that way, we actually, to cut long story short, we were able to develop this unprecedented transformation, which now occurs under mild conditions for a broad scope of substrates. And as we also shown that it works for slightly bigger molecules that are more like functional molecules. But what I like to highlight here, what I really like about this approach, that it's plug and play design where we connect two formally independent cycles. So that means that we can interchange one cycle for another one to obtain a new transformation. So to show you the power of this, for instance, we developed such system where we subject a so-called allylic alcohol, so also very common building block, to two very similar biscatalytic systems where just the functionalization cycle mediated by functionalization catalyst is slightly modified, and in that way we can run reaction to two different products, so we obtain a divergent reactivity. And if you think about this system, it's not only limited to interchanging functionalization cycle, but also to activation cycle. So I believe that in that way, we can open many new reactivities for otherwise unreactive molecules. So what's the take-home message from here? So I think, or I hope, that I showed you that nature serves as a great source of inspiration for developing new technologies, including technologies for organic synthesis. And at the end, I would like to thank this great group of people who is crazy enough to enter the research and try to realize some of crazy ideas. I would like to thank all the funding agencies that enable us to follow those crazy ideas. And I would like to also acknowledge my previous mentors that I was fortunate to work with over my previous career. And last but not least, we have also some opening positions for PhD and postdoctoral positions. So if you know anybody who might be interested, pass the news. And we can, as you can see, we have already some Polish people, we can increase the number. So with that, I would like to thank you for your attention.